You've almost certainly had an X-ray before, right? But do you have any idea how it actually works? Well, today we're going to dive deep and explore the single most common medical imaging tool in the entire world. We're going to follow a single particle of light, a photon, on its absolutely incredible journey, from its violent birth inside a glass tube all the way to the moment it creates a shadow picture of you. So let's get into it. I mean, just think about it. From a suspected broken arm to screening for lung disease, the X-ray is the absolute workhorse of any hospital. It's fast, it's cheap, and the resolution is fantastic. It's pretty much the first stop for countless diagnoses. So understanding how it works is really key to appreciating this cornerstone of modern medicine. But here's the thing that might surprise you. For all its high-tech complexity, an X-ray is really based on a beautifully simple idea. You just have to think of it as a really advanced shadow puppet show. Seriously, the X-ray tube is the flashlight. Your body is the hand making the shapes. And the detector behind you is the wall where that shadow appears. Keep that simple idea in your head, because it is the key to everything we're about to talk about. Okay, so first things first. Where does our beam of light, our X-ray photons, even come from? Well, the story starts inside a vacuum-sealed glass tube, with a process that's both, kind of elegant and incredibly forceful at the same time. It all happens in 5 crazy fast steps, just like you see here. It kicks off with heat. A current warms up a tiny tungsten filament, kind of like an old-school light bulb. That heat causes emission, where electrons literally boil off the filament and form a little cloud. Then things get serious. A massive voltage is applied, causing acceleration, launching those electrons across the tube at insane speeds. They make impact, smashing into a rotating target. And that sudden, violent stop, that's the final step. The creation of X-ray photons. But now, get this. This whole process is stunningly inefficient. A full 99% of all that energy from the electron beam is just wasted as heat. Only 1 tiny percent actually becomes the X-rays we need for the image. And that little fact perfectly explains why the target has to rotate at thousands of RPMs. It's to spread out that intense heat so the whole thing doesn't just melt. So the beam that comes out of that tube is raw. It's unfocused. It's basically a floodlight, when what we really need is a spotlight. So before that beam ever gets near a patient, it has to be carefully refined and aimed. First step is filtration. You see, the raw beam has a whole mix of photon energies, but the low-energy ones, they're totally useless for making the image. They just don't have enough punch to get through the body. All they do is get absorbed and add to the patient's radiation dose for absolutely no good reason. So we put a thin sheet of aluminum in the way. It acts like a bouncer at a club, blocking the weaker photons and only letting the useful, high-energy ones through. Next, we've got to shape that beam. We do this with something called a collimator, which is basically a set of adjustable lead shutters. The best way to think of it is like the barn doors on a stage light. They let us narrow the beam to cover only the specific part of the body we need to see, like a person's chest and nothing else. This is absolutely critical for patient safety, of course, but it also makes the final image way better by cutting down on something called scatter. We'll get to that in just a second. All right, our photon has been born. The beam has been perfectly shaped. Now it's time for the main event. This is the climax of our photon's whole journey, the moment it has to pass through the human body to create that incredibly important shadow. And this, right here, is the magic trick: differential attenuation. It's a fancy term, but the idea is actually super simple. Dense stuff, like bone, is really good at stopping or attenuating X-rays, so it casts a bright white shadow on the detector. But soft, airy tissues, like your lungs, let most of the X-rays pass right through, which creates a dark area on the image. It's this difference, this contrast between light and dark, that lets a radiologist actually see what's going on inside your body. But here's the problem. Not every photon travels in a perfect straight line. Some of them, they go rogue. And these rogue photons, well, they're the villains of our story. They threaten to ruin the very shadow we're trying so hard to create. This villain has a name: Compton scatter. It happens when an X-ray photon smacks into an atom inside the patient and just ricochets in some random direction. Now, if that scattered photon manages to hit the detector, it adds noise. It's like a uniform gray fog that just washes out all the contrast and detail in our image. So to fight this fog, we use a hero called an anti-scatter grid. It's a set of really thin lead strips right in front of the detector, and it basically acts like a filter, absorbing most of those off-angle photons before they can mess up our picture. Okay, so our hero photons have made it. They've navigated the perils of the body, they've avoided scattering. Now they just have one final task, to deliver their message to the detector, which is the device that's going to finally turn their energy into an image we can actually see. For decades and decades, this was all done with a film screen system. The X-rays would hit a special screen that would glow with visible light. That light would then expose a sheet of photographic film, which you'd then have to take into a dark room and develop with chemicals. It was a physical, multi-step process. It worked, for sure, but it had its limits. Today, though, pretty much all systems are digital. Instead of film, we use these amazing flat panel detectors that convert X-ray energy directly into an electronic signal, creating an instant image on a computer screen. The advantages here are just huge. The image quality is better, and doctors can digitally zoom in, change the brightness, enhance details, all stuff that was totally impossible with physical film. It's been a real game changer for getting more accurate diagnoses. So, we have our image, but creating the perfect radiograph? Well, that isn't just about the physics we've been talking about. It's about a constant, really delicate balancing act. It's about navigating this fundamental conflict that sits at the very heart of the entire process. And that conflict is what's known as the radiographer's dilemma. This table lays it out perfectly. Just take a look. Almost every single choice you make to improve the clarity of the image, like see that top row, increasing the exposure to reduce noise, also increases the radiation dose to the patient. You want better contrast using a grid? Yep, that means a higher dose. It is this constant, delicate trade-off between getting a crystal clear image for the diagnosis and keeping the patient as safe as humanly possible. And that leaves us with the one central question that drives the entire field of medical imaging. From how we design the X-ray tube to the software algorithms in a digital detector, every single innovation is aimed at solving this one problem. How do we get more information, more clarity while exposing the patient to less and less risk? It's a challenge that has defined radiography for over a century, and you can bet it's going to continue to shape its future.